So to recap, we know that hot objects emit light by producing a continuous spectrum known as a blackbody spectrum. We know that low-density clouds of hot gas emit light at specific frequencies. And we know that low-density clouds of cold gas in between us and hot sources absorb light at specific frequencies. Let's have a look again at a black hole system with an accretion disk. Can you guess what kind of light we will see from the hot, dense accretion disk? If you said that accretion disks emit blackbody radiation, you'd be correct. However, since accretion disks can become incredibly hot, that is millions of Kelvin, the peak wavelength, according to Wien's law, is not in the blue part of the spectrum, it's not even in the ultraviolet. Accretion disks are so hot that many of them have a peak wavelength in the X-ray part of the spectrum. We also previously learned that the black hole itself emits a type of radiation called Hawking radiation. Unfortunately, scientists have not yet measured any form of Hawking radiation, because the blackbody radiation from the accretion disks of black holes is phenomenally brighter than the light emitted through the Hawking process. In addition, the peak wavelength for Hawking radiation emitted by a solar mass black hole would be a couple hundred kilometers long, which means that no radio telescope on Earth could detect it. We previously mentioned the magnetic fields around black holes, but we haven't delved much into the physics of their interactions with the matter in the black hole neighborhood. The reason is that magnetic fields around black holes are poorly understood. How they form, how they are powered, and the effects they have on the light generated in the black hole environment. We do suspect that magnetic fields are responsible for boosting the energy of particles in the vicinity of a black hole by a process known as synchrotron radiation. A magnetic field exerts a force on electrons and magnetic materials like iron filings. We can easily see the effect of a bar magnet's magnetic field on iron filings by bringing iron filings close to a bar magnet. The magnetic field forces the iron filings to move, and they form a pattern that shows curves that stretch from the north and south magnetic poles. We call the lines that we see in this pattern magnetic lines of force. An electron that moves across a magnetic field line feels a force that pushes the electron into a circular path around the magnetic field line. An electron that has some amount of momentum, also in the direction of the magnetic field line, will experience the same effect, but appear to be moving on a spiral path, circulating around the magnetic field line. Synchrotron radiation was first seen in laboratories that accelerate electrons. These laboratory accelerators are called synchrotrons, so when the radiation was first observed in 1947, it was called synchrotron radiation. One modern synchrotron is the Canadian Light Source located in Saskatoon, Saskatchewan, capable of producing some of the brightest light on Earth. Synchrotron radiation is produced when electrons travel in curved paths, and photons are emitted in the direction that the electron is traveling, like the headlights of a car going around a curve. I prefer to think about the screams produced on roller coasters. They are the loudest during the tightest curves. Since spiraling electrons are moving so quickly, they will naturally emit high-energy photons due to the path's curvature. When radiation is emitted in one direction, we say that the radiation is beamed. This is very different from blackbody radiation, which is equally bright in all directions. Radiation that is equally bright in all directions is called isotropic. Synchrotron radiation is generally associated with the beam emission in black hole jets, which we'll discuss shortly. The brightness of the light emitted at different wavelengths depends on the strength of the magnetic field and the energy of the electrons. One beautiful example of synchrotron radiation can be seen in this true color visible light image of the Crab Nebula. The Crab Nebula is a supernova remnant which has, at its center, a type of neutron star called a pulsar. The pulsar is one of the bright white sources near the center of the image. The faint blue light in this image is created by synchrotron emission from electrons that have been accelerated by the neutron star's strong magnetic field. Depending on how fast the electrons are accelerated by the pulsar's magnetic field, synchrotron radiation can also produce light in the form of radio waves, X-rays, and even higher energy gamma rays. But because this image is only visible light, we can't see those forms of radiation. The red light in the image is an emission line spectrum coming from excited hydrogen gas. This image of the radio galaxy Cygnus A shows a bright point of light and two bright regions stretching out from the point of light to about 100,000 light years in opposite directions. The red color represents the radio emission, showing that the central point of light is the location of a supermassive black hole, and the two bright regions are glowing due to electrons emitting synchrotron radiation. Another process which modifies the electromagnetic radiation present in the environment surrounding a black hole is called Compton scattering. When high-energy photons, like X-rays, scatter off of electrons in a low-density gas, the photons can lose energy in the collision. In Compton scattering, photons collide with electrons like billiard balls bouncing off of one another on a pool table. After the collision, the electron and the photon move off in different directions, with the outgoing photon having lost energy to the electron. The photon, which has lost energy, travels away redshifted, with a longer wavelength than it started out with. Scattering of photons off of electrons also takes place for other types of light, not just X-ray photons like we've seen in our description of Compton scattering. For low-energy photons, like the light visible to the human eye, the wavelength of the photons are much larger and quantum effects are less important. For visible light photons, the collision results in the light changing direction, but doesn't result in a change of color. A similar process to Compton scattering, called inverse Compton scattering, is, well, exactly the inverse of Compton scattering. Instead of a photon losing energy in a collision with an electron, inverse Compton scattering describes a process which results in an increase in photon energy. When a photon collides with a high-energy electron, the electron gives some of its energy to the photon. This increases the energy of the photon, resulting in its wavelength being blue-shifted. In order for inverse Compton scattering to take place, a source of electrons which are moving close to the speed of light is required. Regions near a black hole, such as the corona, are places where inverse Compton scattering is likely to take place. There are many more methods by which light can be emitted, absorbed, and shifted. Some processes, like synchrotron self-Compton emission, are a combination of the ones we just covered. If electrons are spiraling around magnetic field lines at relativistic speeds and emitting synchrotron radiation, the photons emitted can then scatter off of high-energy electrons and gain even more energy. We know our audience loves learning about changes to light, but now we must move on to determine where in a black hole system these sorts of processes dominate.